Right, so in this video I'm going to go through the exam questions from quiz 2. I won't go through all of them, but if there are any that I haven't gone through that you've got questions about, just come and find me. So the first part of the question should be straightforward. You're given the boiling point, you just fill it in on the bar graph. The second part, they ask you to predict what the boiling point of xenon might be using the trend. Okay, so you can see as you go down group 0, the boiling points are increasing. The numbers are becoming less negative. So all you need to do is give a higher temperature than minus 153. Okay, but be careful. You can't go too rogue. If you look at the difference between each element, it's going up by 23, then it goes up by 60, then it goes up by 33. So they're not increasing by huge amounts each time. And on the mark scheme, it doesn't let you go kind of beyond 60. So I think the cap is minus 90. But as long as your temperature is higher, you could go minus 140. They even allow you to do minus 152 and just make it 1 degree higher than Krypton. But just don't make the temperature too high. If you look at the jumps from one element to another, the biggest was 60. That should be fine. That should be fine. Just in question 10, I want to point this one out. You only get a flame of potassium because potassium is the most reactive. So going down group 1, the elements are getting more and more reactive. And when you react potassium with water, there's so much heat given out from that reaction that potassium catches fire and it burns with a purple flame. Okay, but lithium and sodium are flammable too. Okay, we actually use them in fireworks. We do that later on in the course. We look at a topic where we look at the different colours of alkaline metals when you light them on fire. So you will come across that, but they are all flammable. It's just that it's only potassium that's reactive enough to release enough heat to set itself on fire, and that's why you see the purple flame. These other 2 points here wouldn't be relevant to it coming on fire. The 6 marker, okay, please check the mark schemes carefully because they do give model answers and kind of tell you what's required. Just want to highlight 2 things. One, there's 2 parts to this question. You have to describe how the teacher would demonstrate the experiment, and then you need to use the results to give the order of reactivity. In order to demonstrate the experiment safely, okay, you need to use a large trough of water. Now, you might think that might make it more dangerous. If you're reacting it with even more water, maybe there'll be a bigger reaction, okay, but most of the water is just going to be in excess. Okay, the reaction will stop as soon as all the metal is used up, and the extra water is just going to be in excess. It's not going to cause a bigger reaction. To cause a bigger reaction, you would also need more metal as well as more water. And by using a large trough of water instead of a small beaker, if you use a small beaker, a glass beaker, you dropped in potassium, there'd be so much heat given off from the reaction that the beaker could just explode, it could just crack. So you want a large surface area, lots of water in there, because so much heat is given off, you want the water to be able to cool the reaction back down. So you're going to use a large trough of water. These metals again are quite reactive. The teacher wouldn't just pick the metal up with their hand. They're stored under oil, and you'd use little tweezers and you'd pick the metal up and then drop it into the water. You'd also cut very small pieces. You wouldn't take a large lump of potassium metal and drop it into water. I have written a model answer for this in your booklet, and if you look at the mark scheme, it's explained as well. But the other point here to note is how the results give the order of reactivity. You'll notice in the mark scheme it says you can't just copy the results, you need to interpret them. So it says potassium, the bubbling is very fast, sodium is fast, lithium is slow. If you use those words in your answer, you don't get the mark. You have to say potassium's bubbling is the fastest and lithium's bubbling is the slowest. Because lithium's bubbling is the slowest, it's the least reactive. Potassium's bubbling is the fastest, it's the most reactive. So you have to interpret those results. You could say the same for the movement of metal either. The position in water, the fact that they all float, isn't telling you anything. Okay, so again, just check the mark scheme so you can see how to pick up the full 6 marks there. Actually, sorry, in one of the model answers they gave in the mark scheme, the student talks about why potassium is the most reactive in terms of its electron configuration. That's not actually required here. Okay, you don't need to go into that much detail. The next question here is a question on the displacement reactions. You don't actually need to write these equations. I've just written them in so you can see what's happening. So it says bromine, chlorine and iodine are dissolved in water to make aqueous solutions. and then they're added to potassium iodide. So if we look at the first one, bromine is being added to potassium iodide, so that would be this equation here, and you form potassium bromide and iodine. Okay, they're telling you that this reaction takes place because they're telling you there's a colour change, and what they're asking you to explain is why this reaction takes place. Okay, so when we were doing these reactions, we saw that if the halogen by itself was more reactive than the halogen in the compound, they would swap places, and that's what they want you to describe. So you're going to say bromine is more reactive than iodine, therefore bromine can displace iodine. They're called displacement reactions. Displace just means take the place of iodine. And because bromine displaces iodine, iodine is a product and iodine is brown. The second one, you'll say the same thing. Chlorine is more reactive than iodine, therefore chlorine can displace iodine. Iodine is again formed, iodine is brown. And the last reaction, iodine cannot displace itself, so the colour just remains brown. So you're not required to give these equations, you're required to comment on why these reactions are taking place in terms of the reactivity of the halogens. This one I think should be relatively straightforward if you look at the mark scheme. Okay, we haven't done the noble gases because the noble gases is more just some stuff you have to learn. But you've got noble gases are unreactive because they've already got a full outer shell. If you had oxygen in this light bulb, when the metal got really hot, it would react with the oxygen and form a metal oxide. So instead, they replace oxygen with argon. Argon is unreactive because it's got a full outer shell and it's not going to react with the metal filament. That one, I think these should be fine if you just look at the mark scheme. Question 16. So you're given 4 different reactions and you're asked to comment which would be the most violent of the reactions. So in each case you've got a group 1 metal reacting with a group 7 non-metal. To remind you, group 1 metals get more reactive going down the group, whereas with group 7 they're more reactive going up the group. So rubidium is the most reactive group 1 and fluorine is the most reactive group 7. So when you're looking at these, you want something from the bottom of group 1 and from the top of group 7. So if I look at the first reaction, I've got lithium, which is the least reactive, and chlorine, which is the second most reactive, but lithium being there is not really going to help. Then I've got potassium, which is the second most reactive, and fluorine, the most reactive. So that's going to be a very reactive combination. Rubidium, most reactive, but iodine, least reactive. And then you've got potassium, second most reactive, but bromine, second least reactive. So I would say X is going to be your answer there. You've got potassium, second most reactive, going with most reactive. So Y is going to be your most violent reaction. And then you need to explain why. Why are the group 1 metals becoming more reactive as you go down the group? Why are the group 7 non-metals becoming less reactive? So in your booklet you've got 2 model answers talking about how group 1 metals react, about the outer electron being attracted to the nucleus and so on, and the same for group 7. You're basically combining those 2 answers and then you're going to conclude that Y is the most violent reaction. These are based on your displacement reactions. Okay, so when a solution of bromine is added, a reaction occurs, the mixture turns brown. Alright, so when we looked at the colour changes for these, we saw that it's always the halogen by itself. So on the left I've got bromine, on the right I've got iodine. Bromine is an orange colour, so it would have started off orange and then it turns brown. And you're asked, what's the name causing the brown colour? Because they ask you for a name, if you write I2 you won't get it, you have to write iodine. Okay, and it's not iodide, it's iodine because it's not an ion. Okay, it's just the normal element I2, so it's iodine. Explain which substance has been reduced in this reaction. So on the mark scheme they write it in words and they don't give you any more detail than that, but I know your half equations will definitely be accepted. They are in the most recent mark schemes and I do think it's easier. So if we have a look at what's happening here, you're only ever looking at the halogens, all right, when you're just deciding which one's being oxidized and reduced. We saw before that we were always cancelling out the alkali metals. They were spectator ions. They weren't changing going from the left to the right. So they're not involved in the reaction. They just basically watch or spectate. So when you're answering these questions, you're always going to be picking one of the halogens. It's either iodine or bromine. And if we look at iodine on the left, it's in an ionic compound bonded to sodium. And in an ionic compound, it always has a -1 charge. On the right, it's an element, it's got no charge at all. Bromine starts off as an element, so no charge at all, but on the right hand side it's in an ionic compound and will have a -1 charge. So reduction is the gain of electrons. We need to see which one of these is gaining. So iodine is going from -1, so it has a charge, to no charge at all. Okay, in order to, -1 means it had gained an electron, but it must have lost one to end up neutral. So iodine's being oxidized. Bromine, on the other hand, is going from something neutral to something with a -1 charge. To get that charge, it must have gained an electron, therefore it's being reduced. So on the mark scheme, it allows you to say bromine. Okay, you could write Br2 because it's gaining electrons. I would still get in the habit of writing that half equation. Sometimes it's required. So I'd write bromine, so on the left hand side it's just Br2. On the right hand side it's present in an ionic compound, so it would have a -1 charge, and in order to get, and you would have 2 of them with a -1 charge, so you'd need to add 2 electrons, and that's clearly showing that bromine is gaining electrons, and that is why it is reduced. Okay, remember, I'm not going to include sodium in this half equation because half equations only ever include one element. The next one, describe what is seen when chlorine water is added to bromide. Don't be put off by the term chlorine water. That's just chlorine dissolved in water, which is aqueous chlorine. All these displacement reactions are done in water. So I have chlorine, I'm adding it to potassium bromide. It's a normal displacement reaction. Chlorine takes bromine's place, so I get potassium chloride and bromine, and they want to know what is seen. So we saw with these reactions that you're going to see a colour change. The halogen by itself is responsible for the colour, so that's chlorine on the left, which is colourless in solution, and then bromine on the right, which is orange in solution. Okay, make sure you look at the colours in solution, okay, when you're looking at your booklet, because when you dissolve them, they get lighter than their original colour. So it's going from colourless to orange. You get 1 mark for saying colourless, 1 mark for saying orange. If you mention fizzing, you don't get your marks because you're after giving them an incorrect observation, even if your colour change is correct. You're not producing a gas, you're not going to see fizzing, okay, so there's no fizzing, and if you say it, you're not going to get your marks. 34. Explain using the equation how you know chlorine has been reduced. So what I've done, they've told you chlorine's been reduced, they just want you to prove it. So I have taken this equation and written my ionic equation. Remember, if it's covalent, it doesn't change. Ionic, you split it into the ions, but I've gotten rid of the potassiums already because they didn't change. And then bromine's covalent, so it stays as Br2. How do I know chlorine has been reduced? Okay, so I'm going to write myself a half equation. It's Cl2 on the left hand side of the arrow, it's 2Cl- on the right hand side of the arrow. To get that negative charge, it must be gaining electrons, and it's gaining 2 electrons. And again, in the mark scheme, they initially write it in words, but if you look at the additional guidance, it gives you a full 2 marks for this half equation. Even if you didn't balance it correctly, it still gives you the 2 marks. So the half equations will always be the way to go, as long as you can write them, because they will always pick up all of the marks and avoid you having to write it in words. And then underneath, they ask you to write the half equation for bromine from bromide ions, okay? So for the formation of bromine, so bromine relates to the Br2. From the bromide ions, you're starting with bromide ions, but don't be put off by the wording of that. Again, if you just go up to your ionic equation, you're just copying it exactly the same. So Br- starts on the left hand side of the arrow, Br2 starts on the right hand side of the arrow. I haven't changed a thing. And then that's showing the formation of bromine. Bromine's a product starting from the bromide ions. So you just need to fill this in. So it was negative, now it's got no charge at all. Negative means it had gained an electron, but it must have lost those electrons if it's going to lose its charge. Those 4 marks there, if you look at the examiner's comments, they say very few students were able to pick up any of those 4 marks. Okay, so that's something we're really going to target. If we can do the things that others can't, then we're more likely to get those top grades of 8s and 9s. And you know, as long as you know your half equations, they're the same every single time. Once you practice them, and there's no reason you shouldn't be able to do your half equations. The next questions are on, again, the noble gases. This isn't something that you learn specifically. This is kind of like an application question, so you're not going to find this method in the booklet. You just kind of have to use a bit of common sense and application of knowledge. So you're trying to find out the density of a gas, you need to know the mass of the gas, and you're going to divide it by the volume. When they're trying to work out the mass, they first of all take this flask with a stopper and they just get the mass and the mass balance, and then they fill the flask with argon, and then they get the mass again. Okay, so the increase in mass after filling with argon is going to be the mass of the argon. So you just minus one from the other, you'll get the mass of the argon in grams, and then they give you the volume is 250. Okay, just pay attention to units. You're asked for grams per centimeters cubed. The mass you're given is already in grams, and the volume is in centimeters cubed already. Where is it? Volume, yes, is 250 centimeters cubed. If they gave you that volume in decimeters cubed, but the unit down here was centimeters cubed, you would have to do a unit conversion. So just make sure the units that you're given matches the unit that they want the answer in. The next question again is an application, and it's potentially a little bit tricky. They're trying to work out the volume of argon that they've got, and on the flask, this line here reads at 250. So they said, I must have 250 centimeters cubed of argon when this flask is fully full of argon. But remember, it's not, putting a gas in isn't the same as a liquid. If I was pouring water or an acid into this flask, I would stop as soon as the level reached that 250 centimeters cubed line, and I know I would have 250 centimeters cubed of my liquid. But I'm putting a gas in. A, I can't see the gas, and B, even if I could, I've got no way of stopping the gas going beyond that line. So to fill it, you're actually going to fill the whole container. It's not going to stop at that line when you're filling it with a gas. So the error the student made is thinking that you only had 250. The flask can hold more than 250 if you include this bit here, and the gas will occupy all of that space. How are they going to fix the error? They would need to fill the flask up with water or a liquid right to the very top where the stopper would go in, and then they can pour that liquid into a measuring cylinder and work out the actual volume of the flask. So it's going to be bigger than 250, maybe 255. Fill it up with a liquid, pour it into a measuring cylinder, and you'll find out the actual volume of your flask. The next two questions are equations. Again, if you check the mark scheme, that should be okay. These questions are harder than what you had last week. There is quite a lot in this chapter, in particular with the halogens. If you've got any problems, particularly with those displacement reactions and half equations, please come and find me before your quiz.